The goal of this session is essentially to get you familiar with CompuCell 3. I know some of you already know it, but I just want to go over a few basic stuff. So first things, during this workshop, if you discover any bugs, anything that annoys you, just let me know, because like, for example, yesterday I was fixing bugs that, Jim and Giuliano found. So it's actually quite useful to have wider audience looking at the software and, giving some feedback so we can make it better. And we're fairly responsive, so those things will be pretty much fixed on the spot. So having said that, if you install CompuCell, I think you'll have to reinstall it again. The versions that you installed before, the version 4.0, it's functional version, but it had several annoyances, which I think were fixed successfully in the with this update. So if you go to our binaries webpage. Yeah, exactly. So I posted binaries last night. Yeah. And again, I don't think anything we'll be doing today requires reinstallation, but you might actually run into some troubles, especially when you make a typo, you run simulation, and then you find out that you cannot, that you have to restart CompuCell again. So those are the sort of things that I'm talking about. So if you just go to, for example, download page, you scroll down, and you will see the package with today's date or yesterday's date. So it's if you look at the yellow pop-up, it's 2019-08-11. So it's yesterday's date. So you'll just get it. And how many people are using Windows and are using 32-bit machine? If you're using 64-bit machine, that's fine, because for some reason I cannot build 32-bit machine, 32-bit release on this computer. I have to dig in. So, so let me actually show you what I'm doing when I'm interacting with CompuCell, right? So first thing, I'm going to close terminal window. I'm going to maybe close browser window as well. Close tabs. Doesn't matter. All right, so first thing I'm doing on Windows or on Mac, actually, I'm opening terminal, okay? And the reason for this is, there are many reasons. I mean, you don't have to do this, but if you double click on CompuCell installation, and I'm gonna actually open up all the installation, I'm just gonna run first simulation that's loaded. So please don't do that yet. I'm not sure if it will load. No. Okay, let me close it. Very often what happens is that if CompuCell errors for whatever reason, right, I closed CompuCell and the terminal window disappeared. That means that all the text output from CompuCell disappears, right? So if there's an error and you want to send us feedback saying, hey, there's a bug, well, if you double click this shortcut without actually going through a terminal, you won't see what the error is. Okay, so that's, and sometimes CompuCell, it doesn't happen often, but it might happen that it will essentially disappear. So that's why I like doing it like that. So right now, I'm going to go to where my CompuCell is installed. So on Windows, I'm going to CompuCell. There's tab completion on Windows. So if you hit a few times tab, it will autocomplete. So my CompuCell is installed in CompuCell -Py3. So again, for those of you who used CompuCell before we were using Python 2. Right now we switched to Python 3. And the reason is simple. Python 2 is not going to be maintained for much longer. Okay, so nobody wants to maintain Python 2 because the cost of maintaining obsolete Python is way too high. That's why we had to switch to Python 3. And I'm using 32-bit installation because everybody should be using 64-bit installation. I have to type CD. I'm going to go to this directory. While I'm in this directory, I'm typing compusel bad. So essentially what I'm doing is I'm not even typing the whole word. I'm just typing CLM and hitting tab, and Windows will autocomplete. If you are on Mac, what you would do, you would type dot / and compusel, and it would autocomplete. Okay, so dot on Mac means current directory, and then so dot / compusel tab. But we're on Windows, so we don't have to use it. So this is the main interface, right? It's a regular player interface. So I think here I loaded oscillator, SBML oscillator demo. I'm going to load cell sorting for now. And I want to show you, essentially, one of the questions that often pops up is how do you take screenshots, right? So I'm going to show you briefly how to take screenshots. So I'm going to open models, cell sort, CC3D. Sorry, .cc3d file for cell sort 2D. I'm going to run it. It will run, nothing exciting here. But now if you want to take screenshots, right? So previous versions of CompuCell, so if you go to configuration dialog, which is here, and this tool icon, it shows that you have option to save images every nth Monte Carlo step. If you click it and hit OK, and start running, keep running simulation, those images will not be saved. Okay, so what that means is that the option of saving images is already turned on, but you have not selected which images you are saving. So in order for images to be saved, you have to click this camera button. Okay, so I'm going to click this camera button. I can switch to 3D view and rotate the whole thing. Hit camera button, and from now on, if I keep running, I should see 2 screenshots being taken, because I took 2 configurations. I took a snapshot. I told CompuCell to take snapshots of 2 configurations. One is this, and the other one is this 3D. Okay, everybody with me? So now the question is, where does CompuCell write output? And CompuCell writes output to, you know what, I'm going to do that. I hate those explorers, but I will do it. So on Windows, you go to your home directory. So you go to, C drive, then you navigate to users. This is me, and you're looking for CC3D workspace. And on Macs, you do the same. You go to users / your login name CC3D workspace. And here you're looking for a folder whose name is the same as the simulation you're running. So your simulation is called cellsort _2d.cc3d. And we're looking for this folder here. And you're looking for today's date. So every folder is timestamped. And if you go into this folder, first of all, in the output folder, you will always find a exact copy of your simulation, right? Just for reference. So that if you run a simulation, exact copy of your simulation is being copied, so that later on when you want to rerun or you're looking at the results, you know which files were executed. And number 2, you have those screenshots. Those are 2D configurations. We took them at 200 and 300 Monte Carlo steps. and there should be 3D configuration, right? So this is so the lesson for you is, if you want to take screenshots, make sure that you click camera button. Without camera button, this will not work. Now the question is, what happens if you rerun this simulation? So let's rerun this simulation. So I hit stop. I'm going to rerun it. And the simulation runs. So I should see another folder in the CC3D workspace. Okay, so let me go up here. And yes, indeed, there's another folder. And again, I have another set of screenshots. So those screenshots are written persistently. So the screenshot description file is stored. Where is it stored? It is stored in the same place where you have your original simulation. And let me show you where it is. Boy, I wish I knew. I have to check which simulation I was running. If I'm going too fast, please slow me down. So I was in this directory, and I have to go there and see where the screenshot description file is. So I'm going to go to C drive. I'm going to go to my installation directory, demos, models, and cell sort, and cell sort 2D. This is where I was. So notice, there is this screenshot data folder. This is where CompuCell keeps description of screenshot file. If you want to open it up, let me open it up. Oh, it's doing this nasty thing. I should have opened a different editor, but anyway, this is how really Visual Studio is not very cooperative here, but that's not a big deal. How do you open it? Open it, edit it with Notepad++. So this is how CompuCell stores the screenshots. And you know, this stuff is essentially, you know, for developers, and this is internal sort of knowledge. You don't have to understand this. I'm not going to talk about it. But the bottom line is that if you don't want to have screenshots taken, next time you run simulation, just delete this folder. So I'll just hit delete. And from now, did I do the right folder? No, I didn't. Because, yeah, I'm going to delete this folder. And now if I run the simulation, there is no screenshots. So this is like probably your first interaction with CompuCell. You just download it, you open up player, you run demo. Yes. If you don't click camera button, the screenshots will not be taken unless there is screenshot data already in your simulation folder. And another rule of thumb is if you move from version to version of CompuCell, it's a good idea to clean up this screenshot. So if you run the simulation with 3.7 version and you move to 4.0, it's a good idea just to remove, because things might change. So quite honestly, it's not, screenshots are nice because they save images, but in fact they are very limiting, because what if after you finish running simulation you wanted to take different configuration, you wanted to look at maybe chemical fields, but you forgot. And I'm going to show you actually how to do this. Okay. So maybe actually let's do it now. All right. So I'm going to show you how to handle this situation. Okay. So as I said, screenshots are nice, but if you forget to take certain types of screenshots, after simulation is done, everything is gone. So how do we? Is there a better option? And the answer is there is. And I'm going to show you how to do this. So we open up our simulation. I'm going to press step button. So I'm sure you are familiar with this. So CompuCell can either play a simulation so that it runs continuously. I'm going to switch to 2D view so it's faster. Or you can step through simulation using this button. And another thing that's useful to learn with the player is shortcuts, keyboard shortcuts. So let me show you. I'm going to open up player again. So I'm opening player. If I want to open simulation, I can either go to file menu, or you can hit Control-O or Apple-O, depending on which platform you are, right? And this is sort of like common, but I just want to show you that, well, there's this option. So I'm going to open it again, the same cell sort. You know, I'm going to maybe open this one, the one with the growing cells. So I'm going to open a different one. And then what I can do, if I want to start the simulation, I can either hit run or step. But notice, run has a shortcut associated with it. It's Control-M. And step is Control or Apple-E. So either Control or Apple-M, Control, Apple-E, steps. And that's what I'm going to do. I'm going to hit Control-E. Right? And the simulation will get loaded, and it will do this. Right. There's a lot of output being generated. And this output is not generated at every step. I think it's being generated at the start. So you saw a bunch of lines scrolling over the screen, but okay, so now our task is the following. We want to save complete snapshots of the simulation for visualization purposes. How do we do this? Again, you go to this place, and you can uncheck this save image every end Monte Carlo step, because we're not going to be using this. But instead, we're going to select save visualization snapshots every nth Monte Carlo step. And there is a difference, because image is it's a PNG, it's a graphics file that you can view in the browser. Visualization snapshot is not a graphics file. I'm going to show you what we do with that. Let's do that. Let's do that, and then let's hit run. So every 100 Monte Carlo steps, something should be saved. So No camera button for visualization snapshots. Because visualization snapshots are something different. Yeah, exactly. So I think we should have, let's wait maybe, so we have like 4 or 5 of those. I hope this works. One more, and I'll. All right, let's stop. So now let's go to output folder. So output folders are, I have the shortcut in CC3D workspace. And as you remember, the name of the simulation was Cell-Sort 2D, growing cells, mitosis, whatever. And there is a folder here called lattice data. And if you go to this folder, you will see files with VTK extension. So those are your lattice snapshots. Well, let's look at them. Maybe you can see inside. So those files are text files that VTK saves. And using VTK formats, we can encode, we are storing essentially information about all the fields that are present in the simulation. So remember, when we were looking here at this field, right, we were just looking at cells. So all we saw the cells. Now I'm going to show you what to do with this VTK files that were generated, those complete snapshots. So if you go to File menu, you have 2 options, Open Simulation File or open lattice description summary file. So this is what you have to do. You have to open lattice description summary file. This, what is the description is? The extension DML file. So we navigate to output folder and pick this one. And then we treat it as if it was a regular simulation. So we just hit step button. Oh, this is a lot of fun. Yeah, it doesn't work. Let me try again. So this is another feature that I have to work on. So this is those are the joys of porting porting software from one version of Python to another. I'll fix it and I will show the demonstration tomorrow. But essentially, what I want to show you is that you can replay the snapshots as if it was real simulation, right? But then you have all information about every single field and you can take screenshots for that, right? So if you want to generate images based on your simulation, once you have those snapshots, you can replay it as many times as you want and generate images. CompuCell. No, CompuCell. No, you don't use VTK Viewer for that. So for like historical reason, we are using VTK formats, and but you can use ParaView, for example. The problem is that you will have to instruct ParaView how to interpret the fields, and essentially CompuCell player will do it for you. So, all right. So I think this is probably for now as much as I want to talk about the player. There's another component for CompuCell 3D, and it's Twedit. Do people know how to generate CompuCell simulation using Twedit? No. Okay. So first of all, maybe before we go there, let's talk about structure of CompuCell simulation. Okay. So let me go back to the sorry. Let me go back to the demos directory. So we were running this. Let's focus on the recent file that we ran. Cell sort with cells that grow and they divide. So this is the simulation. So let's look at this, the files. So what is this CC3D.CC3D file? Again, I'm going to right click and I'm going to open it in editor. And this is how it looks like. Okay? It's a simple XML file. Is everybody familiar with XML structure? If not, let me explain what XML is. So XML. James, you had very good description of XML. It's essentially a text file with squiggly brackets. And that's what it is, really. XML is nothing else but your old-fashioned text file where you store your data, except it has a certain type of annotations. And those annotations are super helpful because everybody's using them. When you go to Facebook page, if you see how Facebook is coded, a lot of Facebook content is essentially XML. Well, except they don't call it XML, it's HTML. Or not even that, they're using a framework called React. So we're not going to talk about that, but essentially it's a flavor of XML. So everything you see in the modern software right now that's on the web is using formats like that. And there's nothing, there's no mystery here. It's essentially a way to specify hierarchy. So I have elements called simulation, okay? And this element has attribute, version. And it's perfectly fine if I type my attribute. So XML stands for Extensible Markup Language. And what I'm doing here right now, I'm extending it. So every element you see in CompuCell can be decorated. You can put your own attributes, right? Nothing's going to happen. What's going to happen is that those attributes will be ignored. Because the way the whole idea between XML, so to speak, technology is that you create this markup language, okay, that has specific format, right? Save it. And then there is a software that reads this format, right? And the software that parses XML is standardized, so that you as a developer, you don't have to spend time, writing code how to parse XML. There are specific parsers, so that's the benefit. So my simulation element has two attributes, version and my attribute. This simulation element has sub-elements, has children elements. How many children are there? 1, 2, 3. And if you're good, you can even remember names of your children. I don't. So first children element is called XML script that has attribute type. And this field here is called character data or C data. So this is a text. In general, anything in XML is text. If you see numbers, those numbers are read as text. They are later on interpreted as floats or integers or complex numbers or whatever, but everything in XML is text, okay? And this is how we essentially store description about CompuCell 3D simulation. So this CompuCell 3D simulation consists of XML file, which describes static structure of the simulation. It describes how big your lattice is, what type of energy terms you have, what is your initial condition, right? And we'll go over that slowly. Then there is Python script. And Python script is essentially the core of CompuCell, right? So when CompuCell executes, so CompuCell 4.0, when it executes simulation, it always executes this Python script. So whatever you put in this Python script will be executed by CompuCell, okay? And then there is steppable file or extensions modules for CompuCell. So essentially so this is main script that gets executed by CompuCell 3D, and this main script makes calls to auxiliary file, Python file, so that we don't put everything in one file. Okay? And you can have as many those auxiliary Python files as you wish. You can only have one XML and one Python, main Python script, but you can have as many auxiliary Python scripts as you wish. All right? So again, you don't have to remember all that. This is essentially internal structure of how we store information about CompuCell simulation file structure. Yes, absolutely. 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 We can do all those cases. Yeah, I mean, you can create situations like that. I mean, your question is like, can you run into trouble by using Python? Yes, and James actually wrote a book on that, or he's writing a book. Like he might. Of course. Oh, yeah, sure. Yeah, no, absolutely. So bear with me. Next thing, we're going to go to introduction manual, but I want to show you the structure. So this is where your CC3D resides, and if you click here, there is this simulation folder. So remember, simulation, so everything is relative path. So now we're looking for a directory called simulation, and the file cellsort to the field .xml. I'm going to folder simulation, and I'm opening XML document. So this is where the structure of your simulation is. So again, And we'll talk about it over and over, so don't feel pressure to remember everything. You know, there is a pod section where we specify things like, you know, lattice dimension, what's your membrane fluctuation, the neighbor order. We specify energy terms. So plugins usually, so there are two types of plugins. The plugin is a C++ module that has two tasks. It can either compute energy term, so contact energy term, volume constraint, surface constraint, length constraints, those are energy terms. Or plugins can be trackers. What can we track? Well, center of mass, cell surface, cell volume, cell moments of inertia, neighbors, cell neighbors, those are trackers. So two types of plugins, okay? And this is where they are specified. I'm not gonna talk about details right now. Then, if we go back to .cc3d, let's look for this guy, the main Python script. It should be called cellsort2d field py. And this is the file. I'm gonna open it like that. So again, this is the structure, basic structure of the simulation. And always you will type this line, the first line, and the last line. So the last line says, hey, CompuCell setup, run the simulation, right? And this is when CompuCell starts running the simulation. What's in between is essentially instantiation and registration of those auxiliary modules that reside in this file, right? So let's open this. And again, right now we're just like looking at files, we're not going into specific content. And this file, what it does, it essentially allows users to build modules that customize behavior of cells. So for example, what is customization of behavior of cells? Well, I want cell number 22 to start growing at Monte Carlo step 75. That's customization. Or I want to kill that cell at Monte Carlo step 100. That's customization. Obviously, if you were using rigid structure like XML, it would be, I don't want to say impossible, but it would be very clumsy to have this type of logic in markup language. People do that, but it's not a good application of XML. Because sooner rather than later, you discover that you need procedural code. You need to be able to execute short script to say, if something, then something. Or for all neighbors, you know, pick every second neighbor. Yes, you can code it in XML, good luck, but essentially you will recreate programming language in XML. It will be disaster. So, of course, there's another way of dealing with things. You can write declarative languages. You know, declarative languages sound sexy to those who didn't use them, but sooner rather than later, you will discover that in order to understand the execution of declarative languages, you will have to understand the software that executes them. And it's a mess. And I can give countless examples. And often declarative languages are much worse than hated go-to statement. So you've been taught many times that never use go-to statement because you create spaghetti code. Well, declarative languages often are spaghetti code that you have very little control over. Sometimes they work. I'm not a big fan of them. And I saw many people actually being burned by them. So this is the structure of CompuCell simulation. Now, I would like to show you how to build one. I mean, obviously, if you're a Avid Emacs or VI or Notepad++ editor user, you can say, oh, I can copy existing simulation, I can tweak it. Sure, you can do it, but there are better ways. Let me show you. So, just as we ran CompuCell3D, we have in the same directory where we had a executable script for player, there is another script for editor called Twedit++, and I'm going to run it. So Twedit++ is an editor, and it was essentially created as an accident. I wanted to play a little bit with editor engine, and I wrote programmer's editor. Well, actually, the reason was that back then, I don't know, 10 years ago, when you try to get cross-platform editor that would work on Mac, Linux, and Windows, and would be user-friendly, so it would have normal shortcuts, unlike VI, unlike Emacs, right? There was essentially no choice. I mean, the editors were really annoying. And I wanted to have editor that looked the same and performed the same on all three platforms. And I couldn't find one, so I wrote one. And it was just programmer's editor. And then all of a sudden I discovered, why don't we use this editor to actually help CompuCell users? And how can we help CompuCell users? Well, for example, let's say I want to create new project. So I'm going to go to CC3D project menu, and I'm going to hit new project. And you can follow with me if you want. Or we can do it again. We will be doing this again. So I'm going to hit this new project. And then this funny wizard pops up, and it says CompuCell simulation wizard. So here, in the simulation directory, you specify where you want your simulation to be stored. And I have this folder already. It's called CC3D projects. I'm going to leave it like that. Or you know what? How about I change the name and add workshop. Workshop 2019. So that's where I'm going to store my file. And I'm going to call my simulation my first simulation. At the bottom, you have choices, simulation type. You can create a simulation that consists of Python and XML, okay? Or you can create simulation that has Python only code, right? So no XML. So it depends what you prefer. XML has some benefits, and we will show you that, because you can easily tweak XML using Twedit. But if you're fine with Python, you can just switch and choose Python. I'm going to stick with Python plus XML. I'm hitting next button. So next button goes to a screen called General Simulation Properties. And what are those properties? Well, number one, how big is your lattice? Well, it's 256 by 256 by 1. That means this will be 2D simulation. Okay? Boundary conditions. Normally, you would run, well, usually you will run simulation with no flux boundary conditions. But sometimes you want simulation, like if you're implementing flow, you want cells that appear on the right-hand side to be circled back on the left-hand side. So you use periodic boundary conditions, and you can choose this along any axis you want. I'm going to stick with standard properties. Keep in mind that whatever thing is here, you can always change it later in XML. So don't feel pressure to get everything right. Just do the defaults. Now we go to the next screen, and it says how many cell types you will use. Let me say cell type A. Usually you don't want to use short names. So I don't know, I'll use cell A, cell type A, cell type B. You can freeze those cells. Frozen cell is the cell that's like a wall, right? It doesn't move. But it's still, but other cells can stick to that cell with different adhesivity coefficients. So it's useful sometimes. Very little. They shouldn't. Then you can add chemical field. Let's add FGF. And for each chemical field, we can specify solvers. Usually the default solver is diffusion solver. So I'm just going to add it. And then we have cell properties and behaviors. So essentially, cell properties and behaviors screen allows you to customize a few things. It allows you to specify energy terms. So what energy terms we want? We want contact, we want, I don't know, we want volume constraint. And I'm going to choose volume local flags. And each time you see local flags, that means that the parameters of the cell should be managed from Python. Okay, and it's up to you as a user, as a simulation writer, to get those parameters right. And then you have a bunch of trackers. So by default, you have, we're tracking cell center of mass. Let's add tracking of cell neighbors. And let's go to the next screen, and simulation complete, and let's hit finish. So all of a sudden, my simulation is written. If I double click, yes, so the bottom line is you're better off using neighbor tracker because this neighbor tracker is written in C++. So it runs way, way faster than any code. You've heard Andy was talking like 100 times slower. Python is 100 times slower than C++. And you know what? You will be doing lots of loops, and it will be probably that many times slower. So the bottom line is, as much as possible, try to limit iterations or for loops in Python. You cannot avoid them, but certainly if you want to track cell neighbors, you will have to be iterating over cell pixels. There are many cell pixels. And this will essentially kill your performance. James wants to say something.
I mean, the reason the trackers are not turned on all the time is that they take time. And so if you don't need them, having them turned off makes your code run a little bit faster. But you could imagine in the modern world of fast computers, you would have all of them turned on all the time. And that information would always be available. So in a sense, this is a legacy of a day when computing was slower. And so the computational cost of keeping track of certain things was higher. But yes, these are things that report information about the state of the system. But they don't do anything to the system. They simply make that information available to you.
Question.
They're like more efficient functions.
That's right.
I can keep calling that trackers and
So the tracker, so for example, suppose that you have some situation where you actually need to know which voxels in the cell are at the boundary of the cell. Okay, that's a moderately expensive computation to do because you have to keep track of individual voxels on a moment-by-moment basis. And so if you don't need that information, you don't do that computation. If you need that information, you turn that tracker on, and then that information is always available to you. Even things like center of mass. The cells themselves are many voxels across. You have to calculate where the center of mass is. That calculation means summing over the pixels of the cell. That takes some not large amount of time, but nevertheless some time. And so if you don't need it, it will run faster if you don't ask for it. And as an experiment, you could turn the trackers on and off and see how much faster or slower the simulation runs. Most of them don't take a huge amount of time because the way they're written, Bacik's written them in C++ is highly efficient. So it's simply a question of, well, simply. So the answer is that if you need that information, you turn the tracker on, then it's available to you.
I think what I'm really trying to understand is, for example, same by cell migration simulation.
Yes.
Boundary pixels like have higher mobility. So do I need the trackers for me to be able to assign higher mobility to them, or is there like, or I can just call a function, find out all the available boundary pixels, and then apply higher mobility?
Well, so in a CompuCell cell, only the boundary pixels have any motility because by definition, the algorithm doesn't have motility inside of a cell. Only boundary pixels can move. However, if you wanted to do something a little more elaborate where you say something like what Gilberto will show you, which is you subdivide the cell into compartments where you have a cytoplasmic compartment and another compartment that represents the actomyosin leading edge. Then, of course, those actomyosin compartment cells would have a different motility from the ones in the cytoplasm. And in that case, you might very well want to need the boundary tracker to keep track of what's happening. Boundary tracker usually gets used when you're interacting with chemical fields and you want to do something where you have absorption or secretion at the boundary of the cell. The cheapest way to do absorption and secretion is to imagine the cell's a point and do all the secretion and absorption at the center of the cell. It's fast, but it doesn't do a very good job. The second simplest thing to do is to absorb and secrete everywhere over the surface of the entire cell, which usually isn't a terrible approximation. But in some cases, if you really have surface receptors, for example, the absorption is just outside the surface of the cell. In other cases, the absorption might be just inside the surface of the cell. If you want to use those functionalities, then you have to know where the surface of the cell is. So then you have to turn boundary tracker on.
Right, Bruce, another question?
Yeah, so
You can save and then, so this saves complete information about lattices, right? But in addition to that, you can solve your own data. You can pre-process what you're saving, right? You can come up with some simulation metrics that you compute every 10 Monte Carlo step, and the metric itself, maybe it's a number. Maybe it's just a simple, just to give you an idea, a total contact area between all cells of given type with another cell type, heterotypic boundary length, right? So they are not being saved anywhere. They don't save at all. Tracker information is not saved at all, right? It's only for compute purposes. So while your simulation is running, you can ask, what is the center of mass of cell number 68?
oh, this is for interactive.
Yeah.
Simulation as well.
Yeah. Yes, absolutely. And
So you could make a graph.
yes.
I don't know, speed or something.
Yeah,
Versus simulation step. See what's happening.
correct.
So that's
Correct. And we'll cover that in detail, and we'll teach you how to do it in like many ways. And so another question, so I know that everybody is waiting for lunch and I don't blame you, but there was a question about manuals. Where is this material stored? Well, if you go to CompuCell website, CompuCell3D.org, and you go to manuals, everything that I'm talking about right now is stored in this online manual. So it's called Python Scripting Manual for CompuCell3D. Its name can be a little bit deceiving because it has way more than just Python scripting, but essentially, it has information how to transition from CompuCell 3 to CompuCell 4, how to add steppable to the simulation. So for example, I'm gonna be teaching you how to use Twedit. You have this reference here, right? So whatever you need is essentially available here. And if you have some suggestions, like what type of material would be good to add, please let us know because we can add. So there is this manual. Information about what plugins are available. Again, it's available online, right? So you can go and every single plugin, I don't know, neighbor tracker plugin is described in a specific chapter. And on top of that, the new thing that I started adding is this developer manual. So developer's manual, just looking, why is it called, it's for 4.0, I have to update the website. It's also online, and it, for example, teaches you how to build a steppable that computes heterotypic boundary length in C++. Python is slow. If you want to speed, and if you're okay programming in C++ short modules, and again, just like you can create a CompuCell simulation with Wizard with essentially a few clicks, and it takes less than a minute, there is another Wizard that creates steppable or plugin, C++ plugin template within 10 seconds, so that you don't have to code everything by hand. And it works. So there are manuals. Everything is described. James, I suggest we do the lunch now, and maybe after lunch, I will finish the Twedit demonstration briefly, and then we'll move on with Giuliano's material. How does it sound?